Okay, so let's continue on with Center of Mass Linear Momentum chapter. Let me just recap briefly what we're talking about. So center of mass is a kind of very useful concept where you don't have to think about like full geometry of the object. You can basically take some maybe complicated shape or system of particles and then just consider the whole system to be concentrated at one single point. So you can sort of idealize the whole system as a point, and then it would actually move exactly according to the equations that we've been kind of working with so far. And so the way that you work out what this special point is according to this formula for two particles. So if you've got two masses, then you sort of take a weighted average, basically. So if one is heavier than the other, then you weight the positions and then divide by the total mass. For more particles, then you divide by, or you sort of expand that formula, or extend that formula, and then do a weighted average of the position again. It's actually a vector quantity, so you want to do it for all three coordinates if you're in 3 dimensions. And for a continuous body, then actually you can basically change this sum into an integral, and then that formula is basically the same kind of formula, except that instead of having a sum, you have a integral where you are integrating over sort of infinitesimal pieces of some solid object. And so this dm here is this infinitesimal mass, which you can relate to the volume like this. So the rho is the density of the object, dV is the infinitesimal volume. And in general, this is like a multiple integral, which I'm not sure if all of you have done. So usually we look at some simpler problem like this where you don't have to do a multiple integral. If it has some symmetry in one direction, for example, this rod is the same shape along any point in its x-axis, right? So this is why you don't really have to do the 3-dimensional triple integral. You can just do a 1-dimensional integral, because basically the only thing that's if you need to integrate over this x variable, so you definitely need to do an integral over x, but then in the y and z directions, it's just uniform. So you can say that the volume element, instead of being just a tiny cube here, you can take a tiny slice of this rod, and then that is your infinitesimal volume element, and then we worked out last time that the center of mass is in the middle of this rod, which if you've ever done this thing where you take a rod and then you put your finger under it, and then the rod naturally, it's not very good, but the thing naturally slides so that it's balanced on your fingers like this. So this is sort of a natural way that this system tends to go towards the center of mass. So it's in the middle. So basically, another way to think of the center of mass is just at what point can you put your finger under it and then balance the whole thing? This is sort of another way of thinking about it. So where we got up to last time was looking at this particular question, which was to try and find the center of mass of this object, and basically kind of ran out of time last time, so this is where we're going to start off from. But basically the trick in working out where the center of mass of kind of a complicated looking object like this is to first break it down into simpler objects and look at the center of mass. You can kind of more or less by inspection work out where the center of mass of a more symmetrical object is, right? So I think what we did last time was to say something like so if you have a smaller circle which this position has radius r, and then this larger circle. This is r, this is 2r. So in this case, we've got, this is the thing with the hole cut out of it. Now this is equal to the this addition here, I'm just meaning not a mathematical addition really. I'm just saying that, you know, adding this piece and this piece gives you that piece, right? That's all I'm saying really here. So this looks kind of pretty complicated to work out what the center of mass is, but for this one and this one, it's very easy to know where the center of mass is, right? It's kind of obvious. So, for example, here, just by inspection, where is the center of mass of this one, given these coordinates? Here's some more. Sorry? R, yeah. So R, which way? Or, yeah, right, negative R. So it's a negative R, and in the y direction, what is the coordinate? Yeah, just 0, right? Because it's just symmetrical around here. And for this one, we also know that the center of mass of this one, where's the center of mass of this one? Just by inspection. Got to go to 0, which is correct. And y center of mass is also 0. Well, distance, right? Okay. Actually, even for this one, so x center of mass here, this one we don't know. So let's just call it x. But what about the y center of mass for this one? Yeah, it should be 0, right? Because you can see that like this is symmetrical around this axis, right? You flip this way, it's exactly the same shape. So surely the center of mass must lie somewhere along this x-axis somewhere. Okay, so basically what we want to do is to work out what this x is. So this is our problem. Now, let's work out the mass of this one. So we did this last time actually, so I want to go through it again. There's something like, so it's like the area of this thing, this plate might have some thickness, T, and this is rho, that's the density of the object. This one, maybe I'll call this P1 first. Well, maybe I'll call it 2. So this one is twice as big, so it's pi r squared, or it's 2r, so this one's going to be actually 4r squared t rho, right? Okay, and then this one, the mass obviously has to be the difference of these two, yeah? So that's 4r squared, this is just, sorry, 4 pi r squared t, this is pi r squared t, so this is going to be 3 pi r squared t, okay? Okay, so now basically what we're going to do is to kind of consider, instead of considering these things as shapes, you can just consider them to be just some point masses which are just located at the center of here, right? So basically what we're saying here is that So let's call this, maybe let's call that 2, and call that total 1. Okay. Now, what we know from the center of mass formula, get the notation right here. So here, let's call this x1. These are the center of mass position. Okay, this is x2, call this one 2. And this is the total. So the center of mass position in this case, so we got m1 x1 plus m2 x2 divided by m1 plus m2. That's the center of mass position of the combined thing, right? So it's like you've got that one, and you want to find the combined center of mass of both of those, right? We're going to call that thing 1 and call that thing 2. And this one we don't know, right? We don't know x2, but we actually do know what this one here is, right? Because if you combine them, we know that the center of mass should be right in the middle, yeah? So basically all we have to do is to just rearrange this equation for x2, right? So we've got m1 plus m2 times by the total one. Okay, and then we want to find what x2 is here. So what we've got to do is just do m1 plus m2 x total minus m1 x1 divided by m2. And then that will give us what x2 is. So let's go ahead and do that. So m1 plus m2, that's actually the in top there, right? So that's the 4 pi r squared t rho. But actually x total is 0, so I didn't really need to do that. But then minus m1 is pi r squared t rho. And x1 is actually minus r. And we divide all this by m2, which is 3 pi r squared t rho. This thing is 0 anyway. There's 2 minus signs here, so that becomes plus. So we've got pi r squared t rho, pi r cubed. And 3 pi r squared t rho. A whole bunch of things cancel, rho's cancel, t's cancel, pi's cancel. And so this is actually r on 3. So that's r on 3, that's positive. So basically what that means is that, yeah, I mean, as it's sort of implied from this figure here, it's actually a bit to the right, which makes sense because if you cut out a bit of this circle here, then if you wanted to balance this on your finger, obviously if you put your finger right in the middle here, then it's going to fall this way, right, or that way. So you need to balance it a little bit more to the right there. Okay. Makes sense. Any questions? Okay. All right, so let's have a look at this problem. So the figure shows a uniform square plate from which 4 identical squares of corners will be removed. So firstly, where is the center of mass of the plate originally? Yeah, just in the middle, right? So it's just a square, obviously, center of mass is in the middle. Where is it after removal of, say, square 1? And you can say by saying which quadrant it's in. So this one, this one, this one, or that one.
So maybe the quadrant is square 3?
Yeah, so you cut out here, so it's a bit lighter now, sort of on this side, right? So you've got to put your finger in order to balance it a bit more this way, right? And it should be probably somewhere along this diagonal here. So that it's because it's symmetrical along this 45-degree direction. So it'll be probably somewhere around about there. What if you remove both squares 1 and 2?
Maybe on the minus y-axis.
Yeah, so you've cut away 1 and 2. So it's actually kind of symmetrical around y, right? So if you flip this along the y-axis, it's the same. So that means that it has to be somewhere along the y-axis. Well, it can't be in this way, right? Because obviously it's going to tip over if you put your finger under it. So it has to be somewhere around about there. What if you remove squares 1 and 3?
At the origin.
Yes. So again, I think maybe the easiest or the best way to look at these problems is sort of symmetry, right? So in this case, we've removed 1 and 3 here, right? So cut away a piece like here, and cut away a bit like this, right? And then you sort of want to look at so what symmetries does this have, right? So you can see that if you flip it along here, it's symmetrical, but also if you flip it this way, it's also symmetrical, right? So it has to be somewhere along this line and somewhere along this line. So it has to be in the middle. If you remove squares 1, 2, and 3,
So in the contract we square 4 maybe on the y equals to x.
Yeah. Yeah. So if you remove these 3, then so again there's a sort of a symmetry line along here, but now it's obviously heavier on this side, so you better go along this diagonal this way. Yeah. So all 4 squares.
Orange.
Yeah, it has to be the origin. Again, it's sort of symmetrical along x and y too. Okay. Okay, so there's a kind of interesting relation between the center of mass, which you normally don't really think about. So actually, this formula for the center of mass, and if we write it a bit like this, so it's like total mass times by this is the center of mass position, is equal to m1 times the coordinate first particle to so forth. Now say you take the derivative of this equation, right? Okay, then you end up with something like this. Because the masses don't change in time, but positions might, right? So take the time derivative of this equation, then you end up with this one. So it's m times v. Then if you take the time derivative again, then you have something that looks like m total mass times center of mass acceleration is equal to ma1 and ma2 and so forth. And this looks a lot like Newton's laws, right? Excuse me. So what we can kind of sort of deduce here is that we can, well, firstly say what the forces, relate this to the forces, because it's basically, that's the, if we use Newton's second law, then we can say that this is the forces on each individual particle. And then what we can basically say is that this is the total force on the whole system, and that is equal to the total mass and the center of mass acceleration. So basically we kind of have another F equals ma, but this is the total force on the system, and this is the total mass on the system. This is the total, center of mass acceleration. This is actually a little bit like you might think that this is something that we've sort of already done in a way. Like if you remember doing problems like, okay, here's a block and here's another block, and then we could do Newton's laws on this one or this one or this one combined. So what I'm talking about here looks a lot like that. But so firstly, I think the thing about what we're talking about here that's maybe slightly different situation is that generally we were thinking of something that's kind of rigid here, right? So these were just connected to each other. We never really had a situation where sort of one's sort of flying off somewhere. Actually here, we can actually have a situation where it's kind of completely loose, right? So you can equally have some situation where, say there's some particle here, some particle here, some particle here, and maybe there's a force all acting on it. They're all maybe flying through the air with some different forces on it. Basically what this equation is saying is that you can still actually apply Newton's laws, even though they're like kind of disconnected objects. You can still apply Newton's laws kind of to this whole system, so long that you use the center of mass acceleration. So there'll be some center of mass here, and maybe this whole thing's flying through the air like this, and then so the center of mass is moving in some fashion, and so the acceleration that we're talking about here is the acceleration of that position. And so if it applies to something which is completely disconnected, it can also apply to something that's kind of partially connected. It's like floppy, or So basically, you can pretty much apply it to any system that you like. But sometimes it's you need to be clear exactly on what you mean by these variables. So just here's the fine print, if you like, of applying this equation. So when you apply this equation, this force here, of course, so what we just did here is just add up all the forces, right? So in a way, that's the definition of what the total force is. But more specifically, it's actually the net force of all the external forces that act on the system, and you don't have to count the internal forces that are on the system. And so what that means is, like for this, well, okay, actually I'll come back to it. I'll come back to this point. So, but just so that you know what the external and internal force means. External force basically means like the force that's acting on this system of objects, like that's not originating from within this group, right? You've drawn a kind of circle around this. So, there's some force from the outside, say like gravity or something like that, acting on here, that's an external force. An internal force would be something like, say this one is, maybe this one has a rod that's connecting these ones, or maybe it's a piece of string, and then, there's some tension here or something like that. That would be the internal force, right? So, here, what it's saying is that you don't have to count the internal forces, only count the external forces. We'll come back to that point in a minute. M is the total mass of the system. Okay, so I think that's pretty straightforward. Just total mass. So we're not considering a situation where, well, or perhaps the thing that you need to be careful of is that, if you're doing something where, say, system is moving, obviously you have to keep the circle consistent at the beginning and the end, right? So obviously things are going to go wrong if later on, say it starts here and then it goes somewhere else, and then later on you only count 2 of these masses as opposed to 3, then obviously something will go wrong in your calculation. Finally, this A is strictly talking about the center of mass of this system of objects. So it's not the acceleration of these particles individually. That could be actually something different. It's only got to do with the center of mass. So these examples here. So, for example, when a ballerina does this so-called grand jeté move, particular move that you do in ballet, you've probably seen it. So ballerinas, they do this particular move. Well, obviously it looks nice or whatever, but there's a little bit of physics there, because what they're aiming to do is actually to keep the height of their head at a kind of a parallel during the jump. And this kind of creates an illusion that they're sort of floating a bit, because obviously we're used to things sort of moving in this sort of parabolic kind of trajectory. Right? So if something just moves sort of horizontally, it is, it looks like it's kind of floating. Right? Obviously, like you've got a balloon in the air, it just moves to the, just horizontally without following a parabolic trajectory. Has an illusion that it's floating, and so you create this illusion by modifying the center of mass. So in your body, so by putting your arms up or spreading your legs like this, you can shift the center of mass. So the center of mass of the ballerina is actually going parabola, but by kind of modifying the center of mass to sort of compensate for it. So in fact, what she's doing here is in fact making the center of mass in her body actually higher, so that it actually causes her head to actually dip a little bit more. So she would, in terms, if she hadn't done this kind of move, her head would just simply also follow a parabola like this, right? So there wouldn't be anything so strange about, or there would be no illusion, I suppose. But actually, by purposely adjusting the center of mass, actually sort of dips her head, and well, even though she's actually lower, her head is actually lower, creates the illusion that she's sort of floating. This iconic picture of Michael Jordan. I think I read a story once that this is apparently not his idea to do this. It was like sort of the photographer's idea, and trying all different shots, and then the photographer had some idea, sort of inspired from this ballet move, and I don't know, somehow it stuck with it. Okay. Right, so let's talk about these internal and external forces again, because maybe that's the most thing that you need to be most careful about in using this relation. So, like I drew in this example on the board here, so if you have, say, 3 particles here, then potentially there are all these different forces that act on it. So what are all these arrows that I've drawn here? Well, there could be some force on this particle here due to some external force. So some external force acts on this. Maybe it's, could be gravity or some other force. But like I said, there could also be some internal force, which is due to the interaction of these particles with each other. So, for example, this first particle here might feel a force, and so I've written this as F12, meaning this is the force on number 1, particle number 1, but originating from particle number 2. Right? So I'm saying that maybe like these are some charged objects or something like that. So this charge, this object is producing like a force that's acting on here. Like if you've got like 2 electrons or something. But the thing with mutual forces like that is that due to Newton's third law, there will also be a force on number 2, and we know it's actually equal and opposite. So there will be a force actually on 2 due to 1 in exactly the opposite direction of this one. And so this force 1,3, which means the force on 1 due to particle 3, there'll be another equal and opposite force on this one, force on particle 3 due to 1, and there's force 2,3 and force 3,2. But they've also got some external force. Now, if you remember what we did over here, we added up just all the forces acting on the object, right? On the system of objects. So when you do this, what you find is that because Newton's third law says that these internal forces are equal and opposite, actually all these ones in red are actually all going to cancel. So because they're all going to cancel, you can include them. It's not that you're not allowed to include the internal forces. So I said that F net, it's the net force of all external forces, right? It's not so much that you shouldn't include the internal forces, but it's just a kind of a simple trick, if you like, because you know that they're all going to cancel anyway. So just to save you that work, just count the external forces. Right? So if you're going to consider this system of particles and you want to consider what the total force is on the whole system, then you only need to count the green ones, which are forces originating from things which are outside this system of things that you're talking about. Okay, so some examples where you can sort of apply this idea is to look at cases where things which are like a throwing object, which is a non-symmetrical shape. So, so even though this thing might be revolving in some complicated way, if you just look at the center of mass and you just look at the external forces acting on it, then there are actually all kinds of forces that are holding this bat together, right? This piece of the bat is all connected to the rest of the bat, and it holds its shape, so it actually has all kinds of forces acting on each individual bit. But according to this idea, you actually don't really need to think about it. All you need to think about is the external force acting on the whole system, and in this case, the external force is purely due to gravity. So even though you have this complicated shape, and then it might be tumbling and doing some complicated motion, as far as the center of mass motion goes, it's actually very simple. You don't really have to think about any of these complications, and it's not even an approximation. It all, it all simplifies very nicely. Another classic example of this is looking at this projectile motion of fireworks. I haven't looked at this video in a while, but let's have a look. So the center of mass of all these particles here is obviously somewhere in the middle of this whole explosion. So you can see that all these things now start to fall. But actually, if you add up if you look at where the center of mass of all these little fragments are, it would simply just follow the straight ahead parabola. So that's that. Yeah. So those are examples where you can sort of apply this idea. And another example is billiards or snooker, pool, whatever you like to call it. So when you hit the cue ball to and you aim it as a ball, usually you're trying to get it in the pocket somewhere. So it takes a lot of experience to figure out exactly where to hit the ball in order to make it go inside the pocket. And if you play the game, it's not as easy as it looks, right? But actually, if you look at, for example, the center of mass when you hit this ball, actually the trajectory is actually very, it's actually very simple, because say the white ball is coming along here, and if you track the motion of the center of mass at every single point, so this is like a stroboscopic image. So what I've tried to do here is just draw a line between the ball, the white ball, and then this color ball, and then just draw, and usually they're about the same mass, right? So just draw the midpoint of these two. And so this is the first one, second one, and so forth. And if you do that, what you find is that the midpoint, which is basically where the center of mass is just going exactly in a straight line. So it's the center of mass of these two balls actually does not deviate at all. What simply is happening is that there are some internal forces that occur between these two balls, and then they fly apart. But as far as the center of mass goes, it's actually completely unaffected by that collision, and it's unaffected basically because that's an internal force. So there's a force that acts on this color ball from the white ball. Obviously, that's what makes it move. The white ball also deviates, right? It's another force that acts. So Newton's third law pair, and certainly there's forces that have acted on the ball, but as far as this two-ball system, it's actually as if nothing happened. Okay. All right, so maybe we'll just do this one and finish up. So, two skaters on frictionless ice hold opposite ends of a pole of negligible mass. Maybe I'll draw this. Picture. Okay, so this. So Fred is a bit of a big guy compared to this is Fred, Ethel, okay. And so they're holding a pole, and axis runs along the origin and center of mass of the two-skater system. Okay, so this guy is, his mass is twice that of Ethel, sorry. Where do skaters meet if Fred pulls hand over hand along the pole so as to draw himself to Ethel? So firstly, let's work out where the center of mass of this whole position, this whole system here is. So where would it be? Oh, okay, so firstly, it's somewhere sort of a little bit shifted on this side here. And if we say that pole has length L, where is the center of mass? Let's just say that this is x equals 0, and this is x equals L. Okay. And then, so x1 is 0, x2 is L, m2 is m, m1 plus m2 is 3m, so this is going to be L over 3. Okay? So the center of mass position is L over 3 from Fred. Okay. All right, but in terms of the questions, so if Fred is the only one that pulls along the pole, then where do they end up? Okay, maybe we have to leave it for next time. Run out of time. Okay. I'll think about it and we'll start there next workshop. Okay, so see you then on Thursday.